In the name of God, dear friends, ladies and gentlemen, I am happy to talk with you as one of the Iranian researchers. I'm Dr. Davood Fathi from Tarbiat Modares University, Tehran, Iran. First, I will briefly describe my fields of work. One of the areas of research I have focused on over the past 5 years is perovskite-based solar energy structures. A year ago, I defined 2 dissertations in the direction of perovskite-based water splitting systems, and I'm working on them with my research team. Today, I will talk with you about catalysts in water splitting systems for a few minutes. In this regard, I will share with you about results of my research. I first present a short introduction, then about water splitting user solar energy systems. I will talk in the continuation. I will say shortly about photoanode materials for water splitting, then research advances in photoanodes. In this part, my current work will be presented, and in the continuation, I will conclude my talk. Energy, as you know, energy and environment are 2 key issues in modern society, which are necessity for the economic and social sustainable development of the world. In 2018, there is a 79.5% energy economy that relies on conventional energy sources such as coal, petroleum, oil, and natural gas, which are not renewable and environmentally binding. So far, fossil fuels account for about 87% of global energy. Since the beginning of the Industrial Revolution, economic growth has been driven by a continuous increase of power consumption, which has been possible thanks to the availability, high energy density, and low price of fossil fuels. Currently, global demand for energy is growing faster than the capacity and utilization of fossil fuels, which leads to energy shortages. To deal with this problem, there has been a global drive seeking renewable and clean alternatives to fossil fuels. Therefore, today, the development of renewable and clean energy sources has received global attention as an alternative among various candidates. Sustainable solar hydrogen, which directly converts solar energy into chemical energy through photocatalytic semiconductors, could offer a promising solution to meet future energy demand. So the hydrogen is a nice and suitable candidate for us for saving energy. Hydrogen gas with a higher energy density than gasoline, without carbon production, renewable nature, and storage capacity is considered as one of the new energies to replace fossil fuels. Hydrogen can be produced by a variety of methods, as you see in this slide. These methods such as steam modification, partial oxidation of hydrocarbons, coal, gasification, and water decomposition. The focus in this presentation on the water splitting or water decomposition in order to produce hydrogen energy. Being the sun one of the most abundant energy sources, therefore, to electrochemical water splitting is postulated as one of the most interesting technologies due to worldwide water availability, enabling hydrogen as a clean energy vector. Water splitting using solar energy is divided to various categories such photocatalytic water splitting, solar cell powered electrochemical water splitting, solar thermochemical water splitting, and finally was photochemical water splitting that we focus in this lecture and the photoelectrochemical water splitting system and techniques. In this slide, you can observe shortly the schematic of a PLC systems that shows shortly the behavioral performance of the system. One of the main advantages of water splitting systems is to work at lower current densities. This is a nice advantage. Also, in the range of the density current usually is in the range of tenths of milliampere point centimeter square -2. Reducing chemical, this leads to reduce the electrochemical hour potentials, which is necessary for the performance of the system. This results in lower operation voltages in front of commercial electrolyzers, since this is an important feature designed to operate with orders of magnitude higher currents, and thus significantly higher efficiencies could be possible for us. Power coverage efficiency is an important feature for the systems. Lower current densities enable alternative low-cost and earth-abundant catalysts to be used. In addition, PLC photoelectrochemical water splitting systems and approach is a simpler architecture, reducing capital investment costs and electric car transportation losses also. Also, we noticed that the main requirements to achieve competitive PLC water splitting systems, I can refer to one, absorption of broad parts of the solar spectrum, efficient photo-generated electron hole excitation and separation, minimize transport losses to the back contact and semiconductor electrolyte surface, minimal over potential of performing the hydrogen evolution reaction, HER, or the oxygen evolution reaction, OER. Long-term stable operation, which this feature is necessary for the performance in durable time. A scalable device fabrication technique is also important for us, cost-effective and in the final earth-abundant materials. These features is very important for us. In this page, you can see fundamental concepts of PEC water resistant systems. First, at the first steps, we have light matter interaction between the sunlight and the whole system, photoanode as a matter. So the light matter interaction is an important issue for us for the performance of the water splitting system. At the next step, electron hole we have electron hole pair generation. At the third step, charge separation and transfer between the anode and cathode. Meanwhile, catalysis is an important part that facilitates the reaction and performance of the system. In the continuation, we have the water splitting reaction towards the whole and final performance of the system. In here, you can see two important reactions. Say that hydrogen evolution reaction and oxygen revolution reaction. At the right, this relation told us the minimum junction voltage is required to have a high performance for the system, according to that mentioned above. Record values down to 1.4 voltage for a current of around 10 milliampere as a point centimeter square -2 have been obtained. So a voltage of minimum voltage of 1.4 voltages is required for the junction, between the anode and cathode, because the system is photoelectrochemical water respirating system. So the electrical excitation is required and vital factor for beginning the performance of the systems. Here I present a talk and short literature review about photoanode materials for water respirating. Firstly, I refer to metal oxides. Metal oxides have the advantages such as availability, photostability, non-toxic behavior, but usually we face with the issue of having wide band gap. For better performance in metal oxide water restriction systems, using metal oxide in the structure of photoanode in the PSC water restriction system, we have to do, for example, controlling electron structure at surface states, nanoscale material structure. We face with these challenges and issues. Surface decoration with catalysis, metal oxide heterojunctions is important issue for us, band gap modifications. Usually, often we need to make band gap engineering for obtaining a suitable band gap for the sunlight absorption. At the next step, we have porous oxides as the suitable candidates for photoanode materials. Porous oxide structures usually have the advantages such as compositional and structural flexibility. Halide porous oxides are usually used in this slide. In this page, you can see the composition, the chemical composition of an halide porous oxide. These structures have advantages such as high defect tolerance, tunable band structure, spin coating manufacture methods. But in the meantime, we face with challenges such as the crystal structure instability, poor moisture tolerance, a lack of catalytic active sites, inefficient carrier separation for nanoscale unit. These are disadvantages and issues we face with the halide porous oxides. In this structure, chemical composition ABX3 porous oxide, A is a cation, large monovalent alkali metals or small organic cations. B is usually a cation, divalent alkali metals, and X is usually anions, heavy halides. For better performance in porous oxide photoanodes, the PEC water restriction systems that utilize porous oxide as the material for photoanode. For better performance, we should do the following actions. Crystal structure and morphology engineering is usually required. Modification of the chemical component, construction of the heterojunction structure, application of ferroelectric property, construction of plasmonic-based photocatalyst. We usually utilize and apply the plasmonic behavior besides nanoparticle like metallic nanoparticles, Ag nanoparticles, ion nanoparticles that show plasmonic behavior in order to improve the performance of the system, in order to improve the light absorption mechanism. Research in this stage, I refer to recent advances in photoanodes. In the continuation, I will present my research work results that was obtained in my research team. As one of the research advances in photoanodes, I can refer to photoanode with cadmium selenide quantum dot synthesized TiO2 nanorod periodic arrays. Here we have a periodic array of titanium oxide nanorod, which has been sensitized with cadmium selenide quantum dot, we usually use and utilize quantum dots for increasing the surface to volume ratio, so to increase the absorption of the sunlight. Here you can see this advantage and this goal. Here you can see the photovoltaic structure is a periodic array of titanium oxide nanoparticles synthesized by quantum dots of continuum selenide. Typically, I can say that titanium oxide and zinc oxide photovoltaics as two important candidates for this purpose. I mean, as one-dimensional metal oxide semiconductors have gained much popularity over the past decades due to their availability, stability against the sunlight, and non-toxicity. Have been attracted by the researchers during the past years, but in the literature you can observe frequently. Among metal oxide semiconductors, if I like to compare between ZNO and TiO2 semiconductor, I can say that titanium oxide has more advantages, such as proper contact of quantum dots with their surface, chemical stability, low corrosion, low price, and etc., compared to zinc oxide. With all these interpretations and advantages, titanium oxide, due to its large band gap, about 3.2 electron volts, does not have the desired absorption in the visible light range of this semiconductor. This is one important challenge and issue for us in utilizing titanium oxide semiconductor. For this purpose and overcoming this challenge, thick two-dimensional films of titanium oxide crystals and zinc oxide nanowires placed on the film of titanium oxide nanoparticles were used in order to gain a scattering layer of radiation on the photoanode. This configuration helped us to achieve a scattering mechanism of sunlight and overcome the challenge of wide bandgap of titanium oxide that I mentioned above. Quantum dots that I mentioned, I can say, such as cadmium sulfate, CDS, cadmium selenide, CDSE, PBS, PBSE, and indium phosphate, have been placed on the structure for sensitization, in which cadmium selenide has better performance according to the literature in comparison with other quantum dots that I mentioned above. By controlling the dimensions, controlling the morphology of quantum dots, the band gap can be adjusted for better absorption in the visible light range, and the challenge of wide band gap of titanium oxide, we will overcome on this issue in this manner. You can see in these pages the absorption spectrum for various geometry and dimensions of the mentioned and discussed structure. Say that photoanode with cadmium selenide quantum that sensitized TiO2 nanorod periodic array. At the next stage, in this page, you can see another arrangement, photoanode with periodic arrays of Ag nanoparticles, silver nanoparticles embedded into cadmium selenide quantum dot sensitized ZNO nanorods. We use here ZNO semiconductor nanorod sensitized with cadmium selenide quantum dot, and we use here silver nanoparticles for improving the absorption of sunlight. This is another and the second photonode material structure that I mentioned above. Here I can enter to the discussion of perovskite structure. In this page, you can the structure make up from dye sensitization of perovskite type 1, CH3, NH3, PBI3, which is a halide perovskite structure. Due to their superior performance in the field of optical electronics, materials based on the halide perovskite are widely used in energy conversion systems such as solar cells and also water respiration systems, which we focus on these structures in my lecture. However, in direct contact with the aqueous solution, they show poor performance here using CH, as you can see here using CH3, NH3, PBI3, halide perovskite, and dye. We can improve system performance even in direct contact with aqueous solution. We here have sensitized the halide perovskite structure with dye structure in order to overcome the issue of interaction between perovskite structure and aqueous environment. At the next stage, you can see the type 2 structure of dye sensitization of halide perovskite structure. You can see the difference between two structure types. Here, I will discuss the results of my teamwork that also has not been completed, but it is useful to share with you the results of our team. Here we use as the photoanode structure and material AITO substrate and TiO2 thin film. Also a TiO2 nanorad fabricated on this substrate. This is structure 1, which the environment around the TiO2 nanorad, titanium oxide nanorad, is air, can be air or water. I will compare the results obtained for the two environments, air or water. In structure 2, we have perovskite ring around the TiO2 nanoride. The difference between the structure 2 and structure 1 is the ring structure of perovskite placed around the nanoride of TiO2. In structure 3, you can see the structure 1, but the perovskite is completely and totally filled around the nanorod of TiO2 material. I will discuss about the results between and comparison between these three structures. Among these two structures, structure 1, 2, and 3, I said regarding the structure 1, the absorption is only in the range of 300 nanometers to 400 nanometers. So we will not examine this structure alone, and our focus in my lecture and talk will be on structures 2 and 3. In this slide, you can see the comparison between structure 2 on the left and structure 3 on the right of the slide. You can see. The first thing we look at is where the light source is located to get more absorption. For this purpose, we studied the absorption of two sources, 2 and 3. both in air and water, two cases that the environment around the nanorod, TiO2 nanorod is water or air, and the direction of the sunlight from above the structure or below the structure. I will compare the results for these cases.
Hello. Sir, sorry to interrupt, but it would be good, sir, if you can like kindly wrap up because the time is.
Don't you have my voice?
Yes, sir.
Don't you have my voice?
Sir, I'm not able to understand.
Now, can you understand my voice?
Yes, 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 sir. You're audible. You're audible.
Oh.
Yeah.
Can I continue?
Yes, sir. Yes, sir. Definitely. So just that the time is a little bit up, so please kindly look into that. Thank you. Yeah.
You mean I control the time? Okay. For analysis, we have used finite difference time domain simulation method in our obtaining the results. In structure 2, both in water, the left structure, you can see, both in water and in air, the amount of absorption does not matter when the light source is above or below the structure. It does not matter. And only in the range of 300 to 400 nanometers when the source is above, the absorption is better. For structure 3, the absorption both in water and in air is better when the source is below the structure. As a result, therefore, for further comparisons, the source is placed above in structure 2 and below in structure 3 in the future slide that I will explain. I continue the discussion about the important points in the slides. To understand the reason for the reflectance and transmittance, in these slides you can see the absorptance for various geometry of the structure 2 and 3, the height of the nanorods, the thickness of perovskite, the center to center of cells, or the structure, whether is in air or in water. You can see the related curves. Here, through this slide 63, you can see, for example, in this slide 35, for the height of 500 nanometers and the diameter of a nanorod equal to 55 nanometers and the environmental water, you can the absorption and absorbance. From the comparison between these curves, we can conclude that the absorption spectrum and curve is better for water in comparison with the environmental, the air as the environmental around the nanorod of TiO2. The water is better as the final result for the absorption and consequently the performance of the system. To understand the reason for the reflectance and transmittance, you can see in slide 36 and 37 the curves of reflectance and transmittance for the two structures, 2 and 3. Also here, we examine only one of the nanorod dimensions, only for the diameter of 55 nanometer and the height of 500 nanometers, and also in water environment. According to figures, they all follow the same rule. It is not required to check all of the figures. In structure 2, as you can see, the reflectance from the TiO2 side, I mean the above, is less than the ITO side, I mean the below the structure. However, they have the same transmittance. Therefore, the absorption on the TiO2 side is higher than that of ITO. But in structure 3, the results show that the reflectance is higher when the source is above, and the transmittance is the same in both cases. Therefore, it can be said that the reflectance due to the perovskite is more. This is the influence and the impact of the of utilizing the perovskite material in the system. Here is the importance of perovskite structure is evidence for us. So the absorption of the perovskite site is less compared to the TiO2 in structure 3. Also, you can, from slide 38 to 41, here 3 slides, we can see that for P, say that the center to center distance, the distance between the center of cell to the center of adjacent cells in the periodic total structure. The left structure, I mean structure 2, which is the same as structure 2, cannot be fabricated and implemented because if we get together the cells in the total periodic structure, the perovskite will overlap with from one cell to other cells. So for P, the center to center distance equal to 100 nanometers. This structure 2 is not feasible and capable of fabricated and implementing. So in this slide for P, for the value of P is equal to 100 nanometers. Only for structure 3 we have simulated and the curve is presented. For P is equal to 200. In this slide, you can see a comparison between two structure 2, that the sunlight is from the above structure, and for the structure 3, as I mentioned, from the below of the structure. In the structure 3, in all cases, I mean different values of P, the absorption increases with increasing the height and decreasing the diameter of nanorod. The best choice is when the height is 500 nanometers and the diameter is 55 nanometer. For structure 2, as you can see, we have the best absorption in the case that we have a height of 300 nanometers, a diameter of 75 nanometers, the center to center distance, to say that P value is equal to 400 nanometers. In other P values, it is like a structure theory. There is no difference between two structures. These slides show in comparison study by changing and manipulating the dimensionality and geometry of the structure the 2 and 3, and the comparison between the structure to obtain the optimal geometry and material property of the total structure in order to gain an optimal performance, say that efficiency or absorptance for the total structure of the PEC water respiratory system. Here we focus on the photoanode structure, photoanode material in these slides. It should be noted that our simulation results show that the absorption in water is higher than in air. So the environmental, the water environment is better than air. So we can move to what photoelectric chemical water respiratory systems for this reason. For structure 2, as you can see and compare, we have the best case for P is equal to 200 nanometers because the light traps. We have trapping of lights, and as a result, the absorption increases. The enhancement of performance here is due to the trapping of lights, and so the absorption is enhanced. But for the structure 3, the base case is obtained for P is equal to 400 nanometers. This is because for structure 3, we have placed more material of perovskite. This enhancement of performance is related to more material of highlight perovskite around the nanorite TiO2 structure theory, and this result is due to the behavior of perovskite that we focus on this important structure and element in our lecture, in my lecture and presentation. Finally, in slide 42, which this work is under continuation and the results will be completed in the near future. You can see two arrangement of photoelectrical chemical structure, photoanode and together with photoanode inside an electrolyte environment. We can arrange the total structure in two ways. Of course, based on the literature that I mentioned in this structure, the related reference. One is that one arrangement is that the photocathode sticks to the photoanode, in which case we do not speed an external circuit to transfer electrons from the photoanode to photocathode, but in another structure, the left, photocathode and photoanode are separated, in which case we need an external circuit to transfer electrons from the photoanode to the photocathode and also a membrane. At this step, I think my time is over. Hopefully, in the final step, permit me that I conclude my discussion. As the conclusion, PEC, photoelectrical water splitting, has these characteristics, behavior, properties, crystal structure and morphology engineering is needed, modification of the chemical components to the construction of heterojunction structure, application of ferroelectric property, construction of plasma-based photocatalyst surface decoration with catalyst. These are various issues and what we must make to achieve an overall performance, superior performance for PEC water splitting. Here a comparison between two quantum dot sensitization of TiO2 and ZNO nanorods is presented. You can see in the cadmium selenide quantum dot sensitized TiO2 nanorods as a conclusion. To boost light absorption, we should lower the height and have higher diameter and periodic space. We should have a periodic array structure. For the another system that I mentioned, cadmium selenide quantum dot sensitized ZNO nanorods by silver nanoparticles periodic array that I discussed. Also a spherical geometry for silver nanoparticles is needed, and to boost performance, we need density of silver nanoparticles up to 20%, diameter down to 10 nanometers. To have nanoscale diameter, say that the ratio of surface to volume for better reaction and absorption of the sunlight. Also periodic space is needed up to 180 nanometer. About our current results of current work conclusion, we compare two structure 2 and 3. I told us that for the structure 2, the sunlight direction of sunlight should be above the structure, but for structure 3 should be below the structure for better and best absorption, best for the performance. According to curves and simulations obtained from FDDT simulation method for H, say that the height of the nanorods, TiO2 nanorods, equal to 500 nanometers, and the D, the diameter is equal to 55 nanometers, and P, the center to center of the nanorod is equal to 400 nanometers is the best. We have achieved the best performance, but for structure 2, best absorption, best performance will achieve for the height is equal to 500 nanometers. The diameter is equal to 55 nanometers, and the center to center in the between cells in the periodic array structure is equal to 200 nanometers. And also, as I mentioned, better absorption and absorbance and performance will be achieved with the surrounding environmental with water rather than air. Water is better than air. Here you can see the related references. Thank you very much for giving me the opportunity for presenting some of my ideas, thoughts, and results of my research work team. Hopefully, I hope that the presenter can satisfy their opinion and could be useful for the audience of the conference. Thank you very much.